We're going to start chapter 6 now, and our chapter is on linear relations and functions, and our first section is graphs of relations. Before we get going, let's just take a look at a couple of definitions. A relation is an association between two quantities. That just means that two quantities are related to each other, okay? So for example, distance and time. If I'm out jogging, the longer I jog, the further I go. We can represent relations using words, equations, table of values, and a graph. And we're going to be looking at graphs in this particular section. And because we'll be talking a lot about rate is a ratio that compares two quantities of different units. So for example, kilometers per hour, where you're comparing distance with time, height and year, velocity and time. All of these are rates. And I also want to take a look at what a constant rate of change would look like on a graph, what a rate of change looks like when it's not constant on a graph, and when there is no change in rate, what that looks like on a graph. So I've got three small graphs over on the side here, and on the first one, we're going to take a look at a constant rate. Of change. Okay, and when you graph that, that means you're going to have a straight line that goes up in this direction, or it could go down too. Okay, it could go down. Like this. Okay, that would be the red line, right? If the rate of change is not constant, so we'll do that on the next graph. Rate of change is not constant, then the graph would look like a curved line. Okay, it would go up like this, okay, where it starts out fairly slow and then it picks up speed, or it could look something like this. You could start out pretty quickly and then the change slows down. Okay. And on our last graph then, what does it look like when there is no rate of change? Okay, well that would be like a horizontal line, okay? So it would look like that. Okay, so keeping that in mind, let's take a look at our first example. You're asked to interpret a graph. Wakeboarding has grown to be a popular water sport. The graph shows the distance that a wakeboarder is from her starting point on Last Mountain Lake in Saskatchewan. Describe what the boarder is doing. Okay, so for the first part of the graph, AB, since the distance is increasing, the wakeboarder is moving away from her starting point. The change in distance starts slowly at first and then reaches a constant rate. Okay, so AB, that's we're going to start right here at the 0, and we're going to end B here. Okay, and if we take a look at this point, so distance is increasing, right? We're going up on distance, notice that. Okay, and by the way, just to review with you, the y-axis, if you like, is your vertical axis and your x-axis is your horizontal. On our vertical axis we have a distance from our starting point, so this is distance, and on the x-axis or the horizontal axis we have time. So if you notice, the graph is going up from A to B. That means your distance is increasing, so we're moving further and further away from our start point, and that happens over a time also. Okay, so the longer we travel, or the further away we travel from our starting point, in this case, our time increases, right? Okay, so if you take a look at your graph, the first part here is curved, isn't it? So that would suggest to you that you don't have a constant change of rate, right? And if we talk about it in terms of the slope of our line, we say the slope of the line is changing, so we say changing slope. And that means acceleration. two C's, acceleration. Okay, so we start out moving slowly away from our starting point, but you notice it picks up rather rapidly right in this section right here. Okay, so that's quite a rapid change in there. And then the change evens out and then it becomes more constant. Okay, now since for BC, so BC is going to go from B to C, which is right here. Since the distance is not changing, the rider has either stopped or is on a path that keeps her at a constant distance from the starting point. Okay, so that's what a straight line would look like. All right, so two things could be happening here. The rider has either stopped, okay, in other words, the distance isn't changing anymore, or the path that this person is taking could be a constant distance from her starting point. All right, from C to D, which brings us up to the top here, the change in distance increases so that the wakeboard rider is moving away from her starting point at a quicker rate. If you notice, from C to D, the slope is sharper, okay, than from A to B. So if we make a comparison, this slope is steeper than from A to B. Okay, so it means that your distance is changing much more quickly. Okay. Okay, from D to E, since the distance is decreasing quickly, the rider is moving towards the starting point at a fast rate. And notice again, your slope is quite steep, right? So we're now moving back towards our starting point, right? Because our starting point is at 0, which is along, okay, where our distance is 0, which is anywhere along the x-axis, okay? So we're going back to our starting point. And then from E to F, notice again, there's no change in distance again, right? We're not going up and we're not going down, it's constant. So since the distance is decreasing quickly, EF, since the distance is not changing, the rider has either once again stopped or is on a path that keeps her at a constant distance from her starting point. Okay, and the last leg of the journey is from F to G. And notice that the distance is decreasing to 0. So that means that the rider is approaching the starting point again. Okay, and so we're going from a distance which is further away from our starting point back to our starting point, which is, like I said earlier, anywhere along the horizontal axis. Okay. All right, so let's take a look at the next graph. This is your turn, so you could stop the video and try it out on your own. And then start it up again and I'll walk you through it. All right, so your turn. All right, as you can see, I have split the graph up into its parts: A, B, C, A to B, B to C, C to D, D to E, E to F, and F to G. And this particular graph shows the speed of the boat that is pulling a wakeboarder as compared to time. So we're going to compare speed with time this time. And you've been asked once again to describe what the boat is doing. Okay, so if you take a look, from A to B we have constant change, right? You can see that the speed of the boat is going up over time and that it's a constant change, okay? So we say then from A to B that the boat accelerates at a constant rate. Okay, so remember when we looked at or when I gave you the notes earlier, that any straight line that goes up or down would be a constant rate. Okay, so take a look from B to C. There's no change in the speed at all. Okay, so we can conclude that the speed is constant. Okay, and so from B to C, there is no change in speed. So the speed is constant. All right, and then from C to D, notice there's a sharp drop. Notice that the slope from C to D is steeper than the slope from A to B. So we are slowing down, right, because the speed is going from something that is higher to something that's lower. But we're slowing down at quite a quicker rate than we were speeding up from A to B. So from C to D, the boat quickly slows down to a stop. Okay, so you can see that from C, we're at a higher speed, and then when we get back down to our x-axis here, we have a speed of 0, right? Okay, our next section is from E to F, and you can see once again that the boat is increasing in speed, and it's a little slower than from A to B. It's a bit of more, not quite as steep of a slope as from A to B. So we're saying, sorry, this is from D to E. We're saying that it accelerates at a constant rate, but slower than from A to B. Okay, and then the next part of our graph is from E to F, and notice once again we have a constant speed. There's no change in speed. Okay, so from E to F travels at a constant speed. Okay, and then from F to G, notice that the speed is decreasing, right? We're going from a higher speed down to 0. And notice that the slope is not nearly as steep as it was from C to D. So we're slowing down at a much slower rate than we were from C to D. So from F to G, decelerate at a constant rate to a stop. Okay, so let's move on to example 2. And we're going to continue with interpreting a graph. And we have a new situation. We're given 3 different graphs, and we're asked which one of these 3 graphs will describe the scenario that you're given. So the question is, which graph best represents bacteria growth if the bacteria's food supply is limited? Okay, so that means that the food supply is going to run out. Okay, and explain your choice. All right, well, if we take a look at our first graph, this straight line here means that we have a constant growth, okay? And this one wouldn't really fit our situation, because if the bacteria has limited food, then they're going to be eating quite nicely for the beginning, right? But eventually they're going to run out of food, and this graph here doesn't show that we're running out of any kind of food here, okay? So this graph indicates continued growth. Okay, so it doesn't work. Now, if we take a look at graph B, and we have quite a high population here, because notice along the y-axis you have number of bacteria, and then of course on the x-axis we have time. We have quite a high population up at our starting point. And notice that it goes down rapidly, which would suggest that we're running out of food, and then we reach this low number of bacteria, but notice it goes up again, which would suggest that we have food again. But that's not our scenario. Our scenario says that we start out with a lot of food and it's a limited supply, so we're not going to put any more food into our food supply. So this graph shows bacteria dying off when the food supply is high, and then increasing in number. Which is what you wouldn't expect, right? If the food supply was going to be running out. Okay, so that means that, of course, our next graph is the one that we are going to go with. It's the only one left, but let's be sure that we're right about this. So this graph shows that the number of bacteria is starting out to grow slowly, right? And then it picks up in speed quite rapidly, all right? And then it remains the same for a little while because we have constant change here. But then you can imagine once the food supply runs out that the bacteria is going to die off in number, which shows by the decrease in the graph, right? So we have a drop in the number of bacteria. So this graph shows the number of bacteria slowly growing and then growing rapidly. Population remains stable. For a period of time. And then as the food supply ends, and the bacteria will die off. Okay, so the next question is your turn, so if you want to just stop the video and give it a try, and then when you feel that you have the right answer, come back to it. Okay, so in this your turn, we're going to be taking a look at a person's height as the person ages. You've been asked which graph best represents a person's height as the person ages, and then explain your choice. Well, when you think about human development, for the first couple of years of anyone's life, you grow rather quickly. And then it kind of levels off, and you are growing at a constant rate. somewhat. Okay, some people will grow more quickly at certain times than others, but you will eventually reach your maximum height. And you'll stay like that for a number of years, right? I don't know, maybe you finish your growing at 19, and then for the next, 20, 30 years, you're going to stay the same height. And then when you reach your senior years, your height starts to drop off. So let's take a look at our graphs. In graph A, you can see that the height grows constantly up to a maximum, which, sounds pretty good in terms of human development, but notice there's no constant height here. There's no time period for your adult years where you're staying the same height. All of a sudden, when you reach your maximum height here, you just drop right down to whatever it is that you're going to be, whatever height you're going to be at your senior years. So this one probably is not a good choice, right? No. So in the next one, you have some rapid growth, and then it slows down a little, but you're still growing, all right? And then you reach this height, which you stay for a number of years, and then you drop off slightly. So B is a possibility. Take a look at C. You start out slowly, and then your growth increases rapidly. But you reach a certain height, and there's no constant here, right? It's just all of a sudden you reach your maximum height, and then your height drops off. And it's almost like you've grown up, and then you reach your senior years. So this one's not a possibility. For this one here, you grow at a constant rate, and you reach a maximum height, but you don't really stay there for very long. It looks like you just reach it, and then all of a sudden you're going to start dropping again. It's not quite as sudden as graph A and graph C, but still, nevertheless, you're not really maintaining that height for a very long period of time. So this one's not a good choice. So we're left with graph B, which makes sense. You notice that for the first part, you're growing. Okay, when you're quite young, you grow quite rapidly, and so you can see there's a bit of a change in the slope here. But you continue to grow, and then when you reach your maximum height, you stay like that for a number of years, and then when you reach your senior years, you drop off. So when the person is very young, their height increases. When they reach physical maturity, their height remains the same. When reaching senior years, height drops off slightly. Okay, so this ends our discussion. So now we're going to take a look at example 3, where you're going to be graphing a situation. So the scenario is that Josephine leaves her home and walks to the store. After buying a drink, she slowly jogs to her friend's house. Josephine visits with her friend for a while and then runs directly home. Using the distances shown, draw a distance time graph. Okay, so we want a distance time graph that shows Josephine's distance from her house. Explain each section of your graph. Okay, so here's a diagram of the scenario. You have Josephine's house, the store, and her friend's house. From Josephine's house to the store is 1 kilometer, and from the store to her friend's house is 3 kilometers. So the total journey is 4 kilometers. And we're going to graph that on a distance time graph. So here's our graph. So along the y-axis, we have the distance from Josephine's house, and then along the x-axis, we have the time. So the first part of her journey is that she leaves home and walks to the store. So that would be like if I was to go from, I'll call this A to B, okay? And we know that that's 1 kilometer. So if we go to our graph, we can see that from A to B is 1 kilometer. And then I'll draw from A to B on here. And notice it's a constant rate, okay? There's no curve to the line. It goes up at a nice slope. And when we get to B, which is getting to the store, we know that Josephine stops to buy a drink. Okay, so that would be from B to C. She's not covering any distance because she's at the store. So for the short time that she's at the store, she buys. Okay, and her distance doesn't change. Then we know after she buys the drink that she jogs slowly to her friend's house. Okay, so that would be the next part of the curve. So we go a steeper curve then from A to B, because from A to B she's walking. So from C to D she's jogging. So the slope should be slightly at a higher incline. And we'll drop a picture on here to D. And because she's at her friend's house, we now know the total distance is 4 kilometers. So if I draw a line across here, you can see that we're at 4 kilometers, right? So Josephine is jogging at a constant rate. This line segment is steeper than when she was walking because she jogs faster than she walks. So when she's at her friend's place, she stops to visit for a while. So there's no change in distance again. So we have a horizontal line which represents no change in distance. And so we'll call that from D to E. Okay, and so we'll put E here. And so there is no change in Josephine's distance from home while she is visiting her friend. This line segment is longer than the segment when Josephine was at the store, to show that she spent more time at her friend's house. And then we know from there that she jogged all the way home. And so we're going to say that's from E to F. Okay. And this slope should be steeper than from A to B, which was walking, and from C to D, which was jogging. And because she's running now, we should have a steeper slope. We're going from 4 kilometers, which is at her friend's place, to 0 kilometers, which is at her home. So Josephine runs faster than she jogs, so this line is steeper. She covers more distance in less time. And that concludes our example. Okay, so for this your turn, we're going to use the same scenario but switch it up a little. So for the same scenario and using the distances shown, draw a distance time graph that shows Josephine's distance from the store. Okay, so this time it's not from her house but from the store. Explain each section of your graph. Okay, so if we go up to our diagram, we can see that her house is 1 kilometer away from the store. And we want to draw our graph with respect to the distance from the store this time, okay? So when she starts out 1 kilometer away from the store, okay? So I'd mark that on with a point at 1 and A for our starting point, okay? Now she's walking, and she's walking towards the store. So she gets closer and closer to the store, okay? So that means you have to return, because we want to go from the 1 kilometer that she's away from the store to 0 kilometers being at the store, okay? And so we draw a line which shows constant change down to the x-axis, okay? We'll call this B. And so for AB, she walks to the store. Okay, so any point along the x-axis means that she's at the store. All right, well, we know that she stays at the store to buy a drink. So time passes, but her distance doesn't change, and she drinks up her drink. And so we have to illustrate that. So we're going to put another point here. Okay, so there's no change in distance. She's at the store, but there is a change in time because we know she stays there and has a drink. And then we know that she jogs to her friend's place. Now, if we go back up to our diagram, her friend lives 3 kilometers away from the store, okay? So we need to draw a line from C, and she's jogging, so it should be a steeper line than from A to B. and it needs to stop at 3 kilometers, right? So we should be able to draw a horizontal line from 3 kilometers to this point, which we're going to call D, okay? And so, oh, and I should write what BC is, sorry. Okay, so BC then is she's at the store. And then from C to D, she jogs to her friend's house. Okay, which we know is 3 kilometers away from the store. Okay, and she stays at her friend's house. So there's going to be no change in distance, right? So she stays at her friend's house. We'll call that D to E. So even though there's a change in time, there's no change in distance. Okay, and then she runs home. She's running, right? She's not jogging. So she runs home. So we're at 3 kilometers away from the store. So she runs, so it should be a steeper line, right? So she runs home. Now, when we get to the x-axis here, she's at the store, but she keeps running. She's got to run home, which we know is 1 kilometer away from the store. And so the same steepness of line, and then she'll be staying at home, so we can draw a little line like that there, okay? So we go from E to F, and then F to G, and then G and following is when she's at home. So from E to F, she runs to the store, right? And then from F to G, she keeps running to her house. Okay, and then this little flat line here just means that she's staying at her house, right? So the distance doesn't change, only time changes. Okay, and that concludes the Your Turn.